welcome to our meetup. And I see a lot of people here, a lot of new faces, and I'm so happy to see everyone. And this is actually our special event. We're celebrating our anniversary. It's exactly 1 year ago we started this meetup, and we started with the idea of bringing people in data science, machine learning, and artificial intelligence recently in the same place, in the same room, and give people a stage who have something to share and want to present to the community. And the idea is to give everyone, lots of people are going to share their experiences, their knowledge. We all will know more about machine learning and AI, and hopefully we can do better decisions and make a better product. So, and we are growing. Fast forward 1 year, we almost 1,500 people and 600, and that's great. And I'm very happy to see people returning, and for our proposals and for our organizers. So very grateful. So for ones who are new here, we are meeting every month. We usually invite two speakers one night. They give a talk, and we have discussions, and later go to the bar just to meet more and be friends. And our communities cannot be possible without speakers. So here on the screen you can see a form that anyone who works in a field can fill it out, and if you think you have something to share, please fill out the form or reach out to any of us, and we can help you navigate around the topic you can share. So even if you're not sure, fill out the form. We want to bring more people and different opportunity for people in the field to speak. So with our host, Eremin, myself, I am Glenn from the one. So if you have any questions about our meetup, about anything, pretty much reach out to us, and we are happy to help. We have a code of conduct, and it's very short, but this is person-free zone. Please, if you think something is going wrong, please reach out to us. We're trying to make this place to be inclusive and kind of comfortable for everyone. So this is very, very important part. We recently started our Discord channel. Please join. We're gonna start doing more meetups, and also like online meetups. We're gonna run a journal club. We're gonna discuss papers, news. So we want to make this community meetups more frequent, and offline meetups are better organized. So Discord it's live, so please join. Have a chat there. For ones who join from Supermons, there's a QR code. I don't know what it's gives, but people keep asking me, so this is the time when you can scan. The only time someone can scan now.
From far away, it's hard to scan it.
Does anybody want the page?
Alright, I'll put the slide back on the screen on the break, so you'll have a chance to scan. So after each event, and especially this time, we are gathering at the bar a few blocks from here. So not only meeting in sort of like semi-official format, but we are happy to hang out in the bar, and everyone welcome to join some place. Here is our info Google Maps, and our meetup cannot be possible without Capital One, and it's humble note, I'm passing the mic to my Capital One partners.
Nice to meet you. Is this working? You guys seem okay back there?
No, it's bad.
No? I speak louder. Is that okay? All right. Sounds good. Hello. Welcome to the meetup. This meetup is brought to you by Capital One. What's in your wallet? Yeah, very grateful to have them sponsor us here. Go to the next slide. There we go. Capital One is hiring, and because you're at this meetup, that gives you a little exclusive access to get a referral from us and help your odds in the whole recruiting process. So there's QR here, there's QR codes all around here to open up that link, which will give you access to kind of like the steps to go through the referral process. We are also highlighting 3 roles of the ones available that we recommend you check out. So if you're looking into like a senior engineering role or product or machine learning, then I would definitely recommend taking a look at those roles in particular.
I just want to thank Capital One for sponsoring the pizzas, Cleaver for organizing the audio, and then everybody else here for showing up and being a participating audience, because we can't do this meetup without you, everyone. So thank you.
For our anniversary event, we decided to make it a little bit simpler, and we won't have external speakers, but I myself can present page 1 particular topic, so that is very easy. And on the second part, we're gonna have some innovation. We're gonna have our open forum and open discussion. We're gonna turn the seats a little bit, like the front line, and we can talk about LLMs, AI, and in particular, like inference, how to improve LLMs and inference time. And this is our experimental format, so please join. And anyone who wants to participate as in the panel discussion, please reach out to us on the break. And aside from that, anyone can join. And we don't know actually what it's gonna look like. It's we are testing, but we want to make more engagement activity, so that only that someone's talking, everyone listening, they just want to have some conversations. And yeah, so with that being said, we're gonna start with our first speaker, myself, Vladimir Eremin. Quick introduction for someone who didn't know me. I am a data scientist. I work in field since 2016 and mostly in machine learning realm. And my previous project where I worked was about recommendation systems. So I decided to tell about recommendation systems and what they are, and in particular why and how they may go bad, and as a consequence why people can give some really bad recommendations. And I want to use it as an example to talk about a more broader problem in machine learning, which is misalignment between online and offline context, and how choosing the metric on the offline data can result in suboptimal behavior online. And recommendation systems is very handy here, since as a result of that we can see some bad user experience. And we're going to discuss about the metrics and how choosing metrics can affect the performance of the model, and also how it can hide the true performance of the model. We're going to talk about offline and online context in machine learning evaluation, and we're going to talk about explore and exploit trade-offs, which is a cornerstone of the recommendation systems. And we can talk about recommenders without mentioning that. So I'll try to format my talk more like a story rather than facts. And the story is going to be about marketing department and 2 data scientists that are hired to help marketers to improve their recommendation systems. And let's call them Bob and Alice. They both experienced data scientists and they both worked in the field for quite some time. So, and they both know what to do. They gonna get the data from, they're gonna work with the data and come up with some solution, and they're gonna follow through what their solution are and compare them. So let's define the problem first. Usually, their recommendation problem is defined through their user item metrics. And in a database, it's going to look like some data table of the users' items and their event. And in our case, it's going to be conversion, which mean whether or not a user interacted with the product. Maybe they clicked the link in the app, maybe they purchased. For this context, it doesn't really matter. And the task is to predict for what product the user will convert the most. Another way of formulating this problem is probably the most popular one is you have a user item matrix. We want to build the model that will fill the gaps. And then we want to build a system that will select top products for each user and then send it to some form of campaign to execute. So let's turn our attention to Bob. And Bob looked at this data and he decided to go with a straight or like the more obvious solution, which is classification problem. At the end of the day, we want to predict whether or not the user will convert or not, and what the likelihood of the user to convert on a particular product. So classification problem seems like very natural here. And he proceeded that with a regular algorithm in our case. He did some feature engineering, which means he took the long table and converted it into some feature space. In our case, we will have like one feature, and it may be some average purchase frequency or how many clicks the user took on that particular product, or some variations on that. In real life, you may have like hundreds of features. And the target, which in our case is conversion. This data type, we can train the model that will predict probabilities. And those probabilities will correspond to probabilities of conversion at each given product. And Bob decided to use those as a ranks to rank users, and then use a cutoff to select top K items for each user to send to the campaign. And then when the campaign is executed, we record how many converted and we calculate conversion rate. Simple enough. And with this metric, we go back to their step number 2 and refine and optimize the model and iterate until we can see some like noticeable improvement. Very straightforward. Here is another way of how we can see this pipeline. What can go wrong with this approach? Anyone have an idea? Any guess? What Bob's missing here? What am I missing?
Wrong metric. Wrong metric.
Eventually, yes, but in his procedure of selecting data, training model, and executing campaign. You think he may be missing?
I think based on your presentation, it's like it's that the products you choose are also recommended, so that it's a cycle where you recommend the same products, and then that's all the data you have.
Exactly, yes. With this approach, we'll end up in a repeated loop that the same product was recommended. We'll feed back to the model, and the model will learn on the same product that will just eventually will do in the same cycle, and ways to enrich our data set and make the model more diverse. So yeah, also like another problem here that we're actually not recording their scores that was not used in a campaign. So the model produced their, it's not like technically a distribution, but it produced the scores for all product for each users. But we record only the scores that were selected for the campaign and not recording below the cutoff. So, and this is actually tricky, and probably someone can recognize it as our survivorship bias in the data, meaning that we will also end up on a suboptimal model. And it doesn't matter how much we will optimize it, it won't get to any diversity. And this metric can be misleading because it will very quickly diverge from our online context. So on historical data, we will be able to calculate the conversion rate. It may be quite high, but through the time, it will diverge from our online context. So Bob noticed that hard way after some time, and he decided to improve it. He chose not to change the entire pipeline because it may be hard to do, and he decided to make a hotfix. He can add n% of the random items on top of their model selection, in hope that this randomization will enrich our training data set, and eventually through the time the model will be capable enough to capture their diversity and improve the recommendation quality. In our diagram, we can illustrate it as a branching of setting of K random selection along with their best selection. We can also say this through the explore and exploit terms, and that's where I'm introducing those two terms. Where explore is our random selection that practically means that we're sacrificing the accuracy of the current conversion for the opportunity to receive information about our users in this case. And exploit is maximizing the current information that we have to maximize the reward. So Bob decided to start using explore method, but he would manually choose their proportion of their data in the mix. Initially, a lot of explore data set is there more exploit going forward, and he used their precision to control it. So it's a little bit better, but it still does not really solve the problem. And any ideas why?
Because the random data is not actually the accurate data.
Sorry,
The random data that he's using is just a sample randomly picked. It might still not be the entire correct data. of how the products are being used.
That's true. Depending on how we sample their data
Yeah.
set, it might be that we'll end up in our selection bias, that
Yes.
their population of our audience that were selected in random will not represent the entire population of our audience, and the model will be biased toward that. That's for sure one of the problem, and the Bob faced this problem, and he decided to use some like resampling techniques on his training data set, and eventually reduce, and that led him to reduce their training data set quite dramatically. And in my experience, you could reduce almost like a tenfold, which will reduce the bias, but you will sacrifice it for the training data. So that's suboptimal. Konstantin, you want to add something?
Oh, yeah, I was gonna say it's not a very good way of exploring. Like random is too random. You actually want to explore things which are like not so random, but are like more likely to actually be good.
So
Or like you want to explore things that are more likely to be good, or those that you have not much information about, rather than just totally random.
yeah, that's another good point, and I'll actually gonna talk about this in a second. Yeah, pure randomness is a good way of like getting a diverse data set, but in reality, if you think about it, it kind of has a really high cost, because at some point someone will receive quite bad recommendations, and that's the answer, one of the answers to the title of my talk, why you can get a bad recommendations. There'll be no more new information, but generally, yeah, it has a very high cost and high regret, if I would talk more precisely. And if I mean, it's still fine. It's still okay if you know what you're doing, and to know what you do, you really need to have a baseline and measurement, and ideally you want to know the actual cost of this exploration. And Bob used their precision, and he hoped that with the more rich data set he has, like the precision will go high, and he can reduce maybe from 10% to 5% and to 1%. At this point, Alice met Bob, and she said, well, precision it's a good metric, but it's a part of their classification problem and classification context that actually requires both sides of the equation. It requires not only the items that were recommended and converted, which is true positive and false positive, but also false negative and true negative, which are not observed in our data. So at the very best, our metric is incorrect, but actually it's always wrong. It's not the precision that we're measuring, because we don't have the classification context in the first place. We have our recommendation and precisely ranking context that is translated to classification for the convenience. And Bob still not convinced. He said that precision measures how many users converted among them, which is exactly what we are aiming to. So why it's not the right metric. And he said that with enough data we cannot approximate online conversion rate. But is it? Here's another diagram. I'll have a lot of diagrams here, so, but I hope everyone can see it. But generally speaking, there's three sections here. We have offline, online, and the factor space that influence online and is recorded in the offline context. And the user behavior that is captured in the online conversion rate is actually dependent quite heavily on multiple factors. And the most of those factors are not directly observed, and the bread and butter of data science is to find a proxy, a good proxy to measuring them. But we cannot ignore them. That's their important part. And if we can, so offline is a historical conversion rate, online is not only the same. And if you're gonna use the precision only, it may be correlated, it may track online rate for some time, but more likely or not, it will diverge. And the less factors you're capturing from the online context, the faster the divergence between offline and online will happen. So here is another illustration of the difference between explore and exploit learning. The explore-only learning is what was most proposed in the first place, just train the learner and use its prediction to generate recommendations. That's exploit only. We can create a model that will balance between explore and exploit. It will capture a little bit more factors, including novelty, diversity, and sometimes like some temporal factors. But ideally, we want to have our contextual exploit learning that will capture as many factors as possible that occurs in the context of the user experience, and that is the majority of the time the data scientist, and Alice in this case, gonna spend at her work trying to engineer and figure out how we can capture and measure the factors that affect the online conversion rate and incorporate in both the learner and their policy that choose how to select the product for that particular campaign, given their explore-exploit balance. So the second term that I introduced, the policy here, which is another cornerstone of their recommendation system in the context of reinforcement learning. And some might ask, why not use a better, more stable learner that are particularly designed for RexSys problem, maybe SVD or ILS, that are specifically designed to factor the metrics. And generally, I would say yes, that can help, especially if you have strong assumptions that the product, both the product vector and the item vectors are dependent and share some factors that this factor metric factorization model will be particularly helpful. And even some heavy-duty models like XGBoost or neural nets transformers, ChatGPT, can boost on performance, but they are still not solving the main problem here. They intrinsically don't have the policy that address the explore-exploit for the data and for our campaign that aims to maximize their cumulative reward, in our case from that, or through iterations. And actually, the important part here is that we don't have a single campaign here. It's not that we have like a one-shot opportunity to give the best offer for user. In that case, I would say yes, use the model that will produce the highest likelihood and use it. But if we are interested in maximizing their cumulative value from our recommendation system through the time, and that's usually the case because we have some recurring campaign, recurring settings. That's the actual problem that is we have to solve. So at this point we can meet Alice and multi-hour bandit problem, as someone probably recognized where I was leading to. And yeah, multi-hour bandit problem is the part of reinforcement learning that is particularly designed to solve these explore-exploit trade-offs. And Alice said that Alice's point is that it doesn't really matter until, to some point, what learner we use to estimate their probabilities or scores or any produce some ranked order list of items per user. This is a secondary, but primarily we should focus on learning the policy that will dictate at each time whether or not we do need to select the top product or to explore and select some form of random product. And it may be a completely random choice, or it may be a draw from a distribution. And that's why we ideally want to have us estimate some form of the distribution for each user along the product space or the factor space. There are few pillars in multi-hour bandit problem. The first is the number of arms, and in our case it's number of products. For each user we have k arms, k products. We have the reward, the notion of reward. And the reward here is a random variable, meaning that we don't know reward beforehand, but we can collect reward after we pull the lever or send the offer to the user. And the reward may be a binary variable, or it may be some numerical. And we have an objective. And the objective is to maximize cumulative reward over time. And that's the key part, that over time, as I mentioned before. And this framework gives us a tool of how we can design our offer selection for a product. Not only focused on a single campaign, but through their entire period of their product life cycle. The Alice tells us that we want to learn the policy here, and we get it noticed as a P. And we also have a notion of action value function, which is estimate the reward for us. Actually, it estimates the value, meaning that for each user, we can estimate the value for each arm, for each product, and then given those numbers, we can choose which one is to draw. And in the simplistic term, there are action value function can be as simple as the average reward. And if you go back to Bob's example, the feature that he designed can be used as our just average conversion rate through the time, and that can also be served as a mean reward for the multi-hour bandit. And the policy can be, and policy is generally brought into two broad categories. There are like greedy, that means they are like you always exploit their maximum value. So and also the recommendation in the classification settings, from the multi-hour bandit standpoint, it is a greedy function. And there is also like non-greedy, which is there are policies that we are actually interested in. Few of them are the most popular, like epsilon greedy, or upper confidence bound, or like Thompson syndrome. And for you guys who are familiar with that, you can actually recognize that Bob, when he was like trying to patch his solution, he sort of came up with a proto-epsilon greedy strategy, which is select the maximum value with probability E and select the random with probability one minus epsilon E. And but Bob still doesn't control it, and so if you go back to our example on this diagram, we can define this our pipeline through their multi-element banded settings. We have our context vector x and reward that we received from online to offline, and we have our actual value function, which is like expected value of our reward, and in this case it's a simple dot product of the context features and learned parameter theta. I was rushing through this multi-element bandits very quick and probably missing a lot of details, but I was hoping to arrive to this point, to the notion of regret, which is actually the metric that we are interested in. And the regret is defined as a difference between the maximum theoretical reward that we can achieve at all the way up to time t and their empirical reward that we obtained. And that's the metric that is really important, because it can assign us the cost of the exploration and the cost of exploitation. And the idea is that for any decisions where we want to use our maximize value or go to explore, we want to estimate the regret. And here's like an illustration of how three different strategies, like three different policies, are reduce the cumulative reward over time. And this is like a simulation, but the red line is the Wolf version 1, which the greedy strategy. And you can see that the reward was high in the beginning, but then it slowly and then very rapidly decay and converge to some like suboptimal value. Compared to some non-greedy strategies, we see that they gonna have like small rewards in the beginning, but then they gradually find their arms or like the products for each user that have a higher likelihood of conversion and will eventually accumulate higher reward. And the difference between those policies we can measure. Even though that the regret directly we cannot observe, since it involves their theoretical maximum reward, we can find the metric that estimate the regret, or at least like captures it. And that may be gross entropy, NDCG, inverse propensity scoring. I won't go into details right now, but the point is that those metrics use the entire information about the model, and they not their cut off that is like a function of the offer selection. So with that, we will be able to steer our model training toward more like optimal point, as well as control how we enriching our data. And this is like the their central point of my presentation is that for our recommendation system in particular, we want to think globally, we want to think over the longer time period, and we want to capture and estimate the regret. And for WOP, the regret was quite high. So, and also, yeah, in the recommendation problem, it's mostly about the selection rather than the estimate of their scores per se, even though that it's still very important, but yeah, we should focus on the global performance. Yeah, thank you. If there's questions, my colleagues can help.
I'm new to ML, so this is a very basic fundamental question. Okay? So, before ML is so mainstream, this problem existed when people wanted to have better turnover and better sales. So, how was the problem solved then? And how does the solution with ML actually become better? Or what are the challenges around that?
Thank you. So the question was, this problem is quite old, and how modern technology has enabled us to solve it better, right? It's indeed quite old, but their notion of like the multi-arm bandit was formulated quite I think it's from the 20th century, but I may be wrong here, but it's like very old and it's proceeding older than like modern machine learning. But from the question is how modern technologies help it. Generally, their neural networks usually with more data. So what changed, I would say, is that we have more data, and with more data we can train a better model that can capture user preferences quicker. So we right now we have like a shorter this warm-up window when we like exploring their opportunity, like, different options, and it's yeah. The short answer, we can converge to the close distribution quickly, but in my experience, for there some smaller population of audience, because like one of the problems that I have not covered about multi-arm bandits is scalability. In this simplified example, we were referring to like optimizing policy at the user level, but in reality we may have millions or hundreds of millions users, and it just becomes computationally very hard. So there are different ways you can iterate at some user profiles or like user segments level, or like you can have a sequential like sub-optimization and filtering. But generally speaking, even like a simple model, and I tested like Thompson sampling model that relies solely on interactions between users and the product, and it can converge to their some like optimal distribution almost as quickly as using like a XGBoost or on the forest models. So, but it actually very depends on the new problem, because if you have few products that maybe highly correlated to each other, it's one problem. But if you have like thousands of products, you don't have the time to explore them. You will have to be more careful and smart of how you're gonna define your strategy of exploration. And, yeah.
Thank you.
Vladimir, thanks for the detailed presentation. It was awesome. I'm a novice in this topic, still learning and growing. But I was curious if you could talk a little bit more about the development of new cloud computing technologies and how are they assisting the training and the development of machine learning?
Okay, cloud computing. Sure, yeah, I can touch on that. Are you interested in like sort of like Azure slash like AWS
Yeah.
first? Let me think how can tie it to my topic for a second. I mean, the closest that I can tell is I worked with Azure and Azure ML Studio that you can use to deploy your models through their life cycle and manage the entire life cycle of the model, and that helped a lot. But for that particular, for us, is generally you don't really need cloud computing, and as a kind of general rule of thumb, cloud computing has become useful when you have heavy models like neural nets and LLMs nowadays. It's really hard to train one without cloud computing. I've tried to do it on my MacBook. I mean, it still works, but not really. But yeah, short answer, you don't need cloud computing per se to solve Brexit, but more often than not, people are going to use LLMs and deep neural nets. Maybe one of the next topic that I'm going to share is about their one particular architecture of neural networks that solve recommendation system. They're sort of a way how you can use neural nets to do a nonlinear matrix factorization, which actually proves to be more accurate on estimating the user item metrics. And actually, I can scroll all the way to here. Yeah, with these metrics, since they're in methods price, SVD or LS or any linear models were used to decompose into metrics, but their main assumptions is that there's a linear dependency between user preferences and the factors, but it may not always be the case. So neural nets prove to be quite powerful of decomposing matrices as well. So, but yeah, at this point, you probably will need cloud computing, but we can talk offline what it does.
Yeah, thank you.
Any questions? Yeah.
Thank you for the presentation. My question is the YouTube algorithm similar, is similar to what you're explaining here?
Yeah, it's a great question. Yeah, YouTube algorithm, YouTube published a paper in 2014 maybe-ish. There's the main paper in the one of the main papers in the REXIS is YouTube algorithm, and we also used partially YouTube paper in the design of this REXIS in the project that I worked on, but YouTube paper was focusing on the first estimating candidates. So if you have really big and sparse user item metrics, then you have maybe even more items than users. What if they are far? If any algorithms that is described here will be very hard for them to estimate them. It'll just be computationally very expensive. So you have to be very smart of first estimating some yeah, so our best shots or sub-samples, and then run among them. And I think think it's a little bit more advanced topic, I would say. So probably it's logically goes from this topic, and when we want to deploy a Rexis and scale, yeah, that's what the problem we'll face almost immediately.
Thank you.
Yeah.
Thank you. For any companies looking to implement a recommendation system, would you recommend them sort of building the algorithm themselves and following this, or I guess implementing a pre-existing structure and framework for it?
You repeat the last part, please.
Like, would you recommend a company looking to implement a recommendation system and build their own algorithm for it, or like build it themselves, or implement something that's existing for recommendations?
Okay, the question was, should you go implementing from scratch or take something off the shelf and see how it works? Usually, like, in my experience, almost always you're gonna use something that is already implemented. Not only because you're lazy and you don't want to do things from the scratch, but because in a time constraint and a constrained budget, you want to build something like some MVP to test it. If it works, then kind of improve and refine like in more details, because generally you have like more hypotheses to test than the time to test them. So kind of implementing from scratch, and unless it's something kind of very novel or like something very exotic, there are going to be some implementation. But if you want to build a Rexis from scratch, or in general, like some Rexis, you'll still have to make some decisions that is entirely on your own, meaning how you, for example, how you handle like a cold start problem when the new user is arrived and you have no data on them. And it doesn't matter what learner you have and what neural net you train. If you have no data, it's just about like the best guess. And what guess you'll make, it's one of the decisions. You may recommend the most popular product, for example, and that's the majority of the case, and that's why if you're registered in your website, usually like the recommendations that you'll have will sound like the most popular item. Or you can be more creative, for instance, but there's still going to be some decisions that still are going to be on you.
Thanks so much for your time. Are there any metrics that can tell you your recommendation system is under adversarial attacks?
Could you please repeat that?
Yeah, so I wonder if there are some metrics, performance metrics that you can use that would tell you that your recommendation system is under some adversarial attack. By that I mean, let's say there is a campaign, a group of users. Let's say it's just for the sake of example, let's say it's a group recommendation. So a group of users try to confuse the recommendation system by starting to just pick all of the, let's say, horror genre, and they switch suddenly to romance. But this is intentionally done to confuse the recommendation system. How do you approach that? Are there metrics that are wrong to be able to sort of detect that such a behavior is happening?
Thanks. The question was if your system got under the adversarial attack, meaning some group of users or user with some like malicious intent want to manipulate the system for some reason, and how you can know that you're under attack and how you can prevent it or like mitigate. That's a very great question. Personally, I have not worked with that particular problem, but from the literature and like whatever I know, you would usually have a separate system in place that is is designed to handle some anomaly detections, and they may be outside of the recommendation systems entirely, or like have some part of them. So you want to protect your data, and you want to make sure that the data is actually capturing the online context. Otherwise, the adversarial attack will lead to the same problem that I was describing, that was caused by the design choice. But yeah, anomaly detection, it's some additional machine learning that is trained on the data, and usually want to capture this anomalies and somehow prevent the users from the actions. But I'm not aware of any adversarial protection that you can include in the learner itself. If someone else can share, I'm actually very curious to see their things. Any more questions?
Yeah, thanks for your presentation. I have a question. This might be a little bit out of the box, but like, while you when you first were when you were running the model, you see that there was bias. There was bias. So yeah, I would say this question might be out of the box. But while you were running the model, you see that there was bias. Do you think there could be also be some issue due to overfitting, or do you have any idea about that?
The question is why Bob was running the model with a bias?
You were saying that one of the reasons behind it is bias. Do you think that it could be also due to overfitting, that maybe it's not getting the correct, it's not working on
are you asking about other sources of the biases in the model can come from the overfitting on the data that you have?
Yeah.
Yes, that's a good question, and that's also true. I have not touched this in this talk, but yeah, generally speaking, when you're working with machine learning, overfitting is a problem that always at risk, and you need to control for it. And in this particular case, it's very easy to overfit on the data that you have, because not all users will have the same kind of frequencies of their interactions. Some will be more loyal, other users will be less frequent, and you will naturally have more data from more loyal and engagement users than from less engagement. And if you randomly sample your data, you'll have overrepresented more frequent users, and that may not necessarily what you really want to have in your data. So before training the model, there must be some form of sampling the data for training. And thank you. And I think I'm gonna stop here. We've been thank you everyone, and we're gonna take a quick break, and we're gonna return with our panel discussion, and we can move the first line of the chairs and turn them around. The people who in the first line, they actually can still stay where they are, and they can just naturally ahead our participants. And we're going to talk about LLMs and a few topics that cover that, maybe about the Nobel Prize as well. So please join us. We'll figure out how it's going to work. So we're going to take 5 minutes break for pizza and water, and we'll get back. Thank you. Thank you. Do you like this new one?